So now we're going to go over the matrix. I have this file with a box and a rig that's inside of it to help manipulate the matrix and let us visualize how the matrix works when we're manipulating the numbers. I have this file included with the talk as well, so if you want to follow along or look at it afterwards, you should check it out. So I'm going to open up the script editor and show you what the numbers look like before we dig into more of the visualization. Import my commands, and then here I'm going to get the XForm, use the XForm to query the matrix from the cube. Then I print the matrix. This is a standard output that you would get from printing the matrix of an object using the XForm command, but you get 16 numbers, and the matrix is really a 4x4 matrix. And because these 16 numbers just come across as a list, it makes it a little hard to work with them. And so an easier way would be, here I print them out in sets of 4. So here I take the first 4 numbers, put them in a row, the next 4 numbers, put them in a row, and so on and so forth. And I print these out. And this gives us a 4x4 matrix, visualizing these 16 numbers as such. And this lets me start talking about some more definitions. When we have the numbers from left to right, these are considered a row. The numbers going from up and down are considered a column. The first thing I'll mention is the very last column of this matrix are numbers that we won't be using and we don't need right now. The first 3 numbers in the row are the most important numbers, and as you can see to the left, I've marked each of these rows with a letter of X, Y, Z, and T, and that is because the first row represents an X vector, and interestingly enough, it has a number of 1 going the X direction and then 0, 0. The next row is 0, 1, 0, so it represents the Y vector. And the third row represents the Z vector. And then the fourth row represents a translation, which right now is 0. Now if we jump back into Maya, our box is currently represented, has this object here representing its matrix. If we select the center object that is representing its translation, and down here at the bottom I show matrix row 4, column 1, row 4, column 2, you can see that the matrix is 0, 0, 0. Now if you select the X vector, this is the matrix row 1, column 1, row 1, column 2, and it's 1, 0, 0. And then the Y is 0, 1, 0, and the Z is 0, 0, 1. So because I'm printing these numbers here in the channel box, you actually don't even need to go back and print the matrix. You can actually see them just by moving stuff here. Just note that the top numbers do not represent the matrix. The bottom numbers that are yellow do. So the first thing I'm going to do to visualize is the translation portion. And the translation part is the simplest, because it is always just basically the numbers are what you get, and they're very easy to understand. And so if I move this translation off, you get negative 1.3 and 1.5 and 0.9. And that's exactly what you see in the matrix. So that's all that is the fourth row. If you were to go back into the script editor and print this out, you'd see that the fourth row has all of the numbers, and the other rows are still as if they haven't moved. This one has a very tiny, tiny movement for some reason. I don't know why. But next, I'll go over how you scale your object. So after we have moved it, let's say we took the X. The way that scale works in a matrix is if the vector is a non-unit vector, so it's not normalized, that defines the scale. So if I set the vector to be a length of 2, that means that the box, if we look at the box, its scale x is 2. So if we wanted to make the box be twice as large, we just set the scale, set each of the vectors on the matrix to 2. Now the scale of the box is 2, 2, 2. So if we go back into our script editor just to kind of see what that was again, it's 2, 0, 0, 0, 2, 0, and 0, 0, 2. So that is why those vectors can represent both. So that's how they are for representing scale, but they can also represent rotation. So if we select the center translation object, you can rotate that object, and you are rotating the cube. And when this is rotating the cube, what it's really doing is rotating each of these vectors. So if we select the x vector, you can now see it says 1.76 and 0.89. It has all these different numbers, and same for the y vector. It's showing negative 0.9 and all that. If we go into the script editor again and just print it out so we can see them all at the same time, got a mass of numbers and they're all doing different things. But when we really break it down, it's pretty simple. It lets you see, if you were to draw these out as locators, which is basically what is going on here, you can see the only thing that's happening is now our vectors are pointing in new directions, and that is defining the rotation of our object. Now, one other thing that we can do that's a little funky, but because we have this rig, it's really easy to do. If the matrix gets off, like one of the vectors were to point in a funny direction, that basically makes our box get really funny looking. And because the matrix is now all, it's all weird, because it's not like 90-degree angles. And you can see what it would take to do that. You would have to set the scale to 2.7, 1.4, and 2, so you'd have to give it non-uniform scale. So that's probably not what you want to do most of the time, but at least you can see what happens when you move the vectors around. So that's about it. The matrix is, if you can wrap your head around how this works, it's pretty simple. The matrix basically just has these 3 vectors on top, and those represent the rotation, and then before they get rotated, you have this translation. So you get your translation from world 0 to here, and then off of that you get your vector, and that defines your rotation of your object. So that is a matrix.